All right. I would like to do a quick walkthrough with you for this midterm one exam, just to make sure well, even if after the exam you can fully understand what the answer key said. So I hope you all know like where to put your name and ID, and let's get started. The first problem here are multiple choices. Well, the first question asking for the unit of this hypothetical state function, or Helmholtz free entropy. It has the same unit as entropy S, or as internal energy over temperature. So naturally, it will have the unit of joule per Kelvin, which is C. Then just write out the full equation for the entropy, the phi, and it is given that this state function is a function of S and T. So we can write this one as S and T. So we have two dependents, right? We only need to put B here. 1, 2, 3. This one actually has two answers. So both B and D are correct answer. So both B and D are counted correct for this problem. Molecular mass. So we went over this concept in class. When we're talking about the molecular mass, we're talking about its actual mass of formaldehyde. So the unit for molecular mass is AMU, or atomic mass unit. Then which of the following changes in function is not zero for a cyclic process? So for a cyclic process, a state function, the change of a state function would be zero. So U, H, and V are all state functions. So D is our correct number. Okay. Moving on, 2 to 1, every isolated system is closed. So this one is correct. Remember, isolated means no matter or heat exchange between the system and the surrounding, where a closed system only requires no material exchange. A homogeneous system must contain more than one element. So this one is false. Remember our ice water example, right? We can have both ice and water. And similarly, you can imagine something like a liquid nitrogen and gas nitrogen in coexistence. Reversible PV work in a closed system always equal to negative P delta V. So this one is also false. So if you think about it, what we have is dW ReV equals to negative PdV. All right, so at constant pressure, when we take the integral on both ends, we have ReV equals to negative P delta V. But when it's not constant pressure, the ReV will equals to the integral of PdV. A process with no heat transfer between the system and surrounding must be an isothermal process. No, this is an adiabatic process. And an adiabatic process is not necessarily isothermal, right? So if you remember, for ideal gases, for the adiabatic process or adiabatic expansion or contraction of the gas, we have the following equation. I mean, it's okay even if you don't know this expression or this equation. Just know a adiabatic process is different from an isothermal process. The total heat in the Carnot cycle is zero. So this one is definitely wrong because your heat is not a state function. All right, let's keep going. Now, short answer problems. First one, hypothetical gas obeys equation of PV equals nRT A plus 3BP, where A and B are constant. Write the isothermal compressibility. So this one is a simple derivation. So for chi, we want the partial derivative of V over P at constant Tn. So the first thing is to write it as V, an expression of V. So we have nRT times A plus 3BP over P. And we can fully write it out as A nRT over P plus 3B nRT with the P cancel out. And then taking the derivative, we have chi equals to, well, this term do not have a dependency on P, so it goes to 0 when taking the derivative. This term, well, when you're taking the derivative of P, it becomes like negative ANRT over P squared. So our chi becomes negative V over 1, that's where that V over 1 is. We have our constant ANRT and the derivative of 1 over P squared. And chi equals to ANRT over VP squared. Now we do not want to have V in our expression, so let's further write out to be ANRT over P squared times nRT, well, 1 over V, so that is P nRT A plus 3BP. And our P cancel out with P, nRT cancel out with each other. We end up with an expression of P times A plus 3BP. On top we have A. Let's write that expression on the top. A plus 3BP. Okay, now let's keep going. Next question. A Carnot cycle heat engine has an efficiency of 60%. That does 6 kilojoule of work per cycle. So what we're saying is a heat engine does 6 kilojoule of work per cycle. So the system or the heat engine does work on the surroundings. So our work will be a negative number, negative 6.6, 6.00 kilojoule. Now we know what work is, we know what efficiency is, and we have the definition of efficiency being absolute value of work divided by QH. So in this case, QH equals to absolute value of work divided by efficiency, which gives me 10.0 kilojoule. As of our QC, we have our entire heat engine following the first rule of thermodynamics. We have delta U equals to Q plus W, and here Q equals to QH plus QC. So what we have is QH plus QC plus W equals to 0. So naturally our QC is equals to 4.00 kilojoule. All right, next up. The heat of vaporization of benzene at 80 degrees Celsius is 30.7 kilojoule per mole. Calculate delta S when 10 grams of benzene vapor condense to liquid benzene. So first of all, we're asking to calculate delta S. So we know that delta S for a reversible process. So now we know it is reversible because that's what the what the vaporization point for benzene is. That equals to Q reversible over T. And in this case, our Q reversible equals to Q condensation equals to negative Q vaporization. And now our Q vaporization equals to, well, we have 30.7 kilojoule per mole. We do not have 1 mole of benzene, so we have to convert that. That gives me 3.94 kilojoule. So our delta S condensation equals to negative 3,940 joule divided by the temperature, which is 80 plus 273 Kelvin. That gives me about 11.2 joule per Kelvin. Negative 11.2 joule per Kelvin. Right. Next up, 3-4. The question asks you for calculate Q, W, delta U, delta H, and delta S for a reversible isothermal expansion at 300 K of 2 mole of perfect gas. We know the initial volume and final volume. So first thing first, when we know it is isothermal expansion of a perfect gas, we can instantaneously write these two terms to be zero. So remember, for perfect gas, your internal energy and enthalpies are only dependent on temperature. So for a process where temperature is not changing, this term remains zero. Now for a reversible process, we can calculate the work that's being done by using negative PdV. All right, and here for ideal gases, we can write it to be negative nRT over V dV, or we have negative nRT from V initial to V final 1 over V dV. So plugging the numbers, we have 2.00 more. We want our final answer in joule, so let's pick our correct gas constant, 8.314 joule per mole per Kelvin, times the temperature, which is 300 Kelvin, and you take the integral of final volume, which is 2000 minus initial volume, which is 1000. So doing this calculation, we have our work to be negative 3458 joule. Right? Or in this expansion process, your system is doing 3,458 joule of work to its surrounding. And in the process, because of first law of thermodynamics, we have Q plus W equals to delta U equals to 0. So your Q must equals to 3458 joule, while your system is absorbing heat from the surroundings. And then the calculation of delta S becomes quite straightforward, equals to Q over T as this constant temperature. So we have 3458 joule divided by 300 Kelvin, and that's 11.5 joule per Kelvin. Okay, next up, comprehensive problem number 1. Now we have all these systems will continue to come back to this figure. We're from 1 to 2 is an adiabatic process, or you can instantaneously write down Q equals to 0. We're from 2 to 3, that's an isochoric process. From 3 to 4, it is adiabatic, and from 4 to 1, it's again isochoric. So for isochoric reversible process, your work always equals to 0. For adiabatic processes, you have Q equals to 0. And here we know some of the like pressure and volume of some of the states, and you will be asked to solve for some of these unknown pressure or temperature or volume. But before that, let's look at the first problem. Considering the process from state 1 to state 2, we want to know whether or not the system doing work on the surrounding or the surrounding doing work on the system. So in this case, from 1 to 2, we see the volume is increasing, right? So that tells us the change of volume in this process is a positive number. So our W equals to negative P dV. Since pressure is positive, dV is positive, so work is a negative number. And a negative work means my system is doing work on the surrounding. Right. And let's consider in process 4 to 1. So for process 4 to 1, it is asking of the heat transfer between the system and surrounding. So between 4 to 1, we have work equals to 0, so our heat of 4 to 1 essentially equals to delta U from 4 to 1. Now, how does our internal energy change? For a ideal gas, our internal energy is only dependent on temperature, and as a matter of fact, we know that U equals to 5 over 2 nRT. The one has a higher temperature or higher PV comparing to 4, so naturally one has a higher internal energy. So from 4 to 1, the internal energy increases, and that means our Q from 4 to 1 is a positive number, or the surrounding transfer heat to the system. All right. Next up, calculate heat for the process state 4 to state 1. Now, again, like what we said, right? So our work from state 4 to 1 equals to 0, and our Q from 4 to 1 equals to our delta U from 4 to 1 equals to U1 minus U4. And in this case, we have U equals to 5 over 2 nRT, or in this case, because it is an ideal gas, we can rewrite our T equals to PV equals to N over NR, and this NR cancel out, so we have U equals to, well, 5 over 2 PV. All right, so here we're just using PV equals to nRT. Now it becomes quite obvious because we know what our P1S V1 and P4 V4 are. So we can calculate our U1 equals to 5 over 2 times P1 V1 equals to 5 over 2 times P1 V1, that's 4,000 ATM centimeter cube, or 10,000 ATM centimeter cube. U4 equals to 5 over 2 times P4 V4. Let's come back. P4 V4, that product equals to 2,000. Times the heat capacity, we got 5,000 ATM cm surge. All right, so naturally Q421 equals to U1 minus U4. That gives us 5,000 ATM centimeter cube. Okay, let's keep moving on. Fourth 4. Calculate the temperature and pressure of state 2. Now, in this question, it becomes a little bit anti-intuitive because we have what we have in state 1. We have P1, V1. For state 2, we know our final volume, but we do not know what its pressure is, and we do not know what its temperature is. But what we do know is that between your state 1 and state 2, this is a adiabatic process. So recall what we have. What we have here is, well, first of all, we have PV equals to nRT, so you can calculate T1 from P1V1 over nR. Also, what we have is for a adiabatic process of an ideal gas, we have T2 over T1 equals to V1 over V2 times, well, as a power of nR over Cv. And as we read from the hint, we have du equals to Cv dt for ideal gases, or U equals to Cv delta T. Now in this case, delta U equals Cv delta T. In this case, we can easily read Cv equals to 5 over 2 nR for the ideal gas. All right. And now what we know, we can calculate T1, and we have V1 equals 2000, V2 equals to 6000. N is a constant, R is a constant, Cv is something we know. So we have everything we need. So let's just calculate T1. So T1 is P1V1 over nR, and we're just plugging numbers. So P1V1 equals to 4000 ATM cm cube. Let me double check if I have that correct. 2 times 2000, yes. Divided by nR, we have, well, one more. So let's plug in that one more. R, because we have ATM centimeter square, we want to use our correct gas constant. Right. So plugging numbers, we have 48.7 Kelvin. And then plugging this T1 to that equation above, we have T2 equals to T1 times 1 over 3, or 2000 over 6000, and R over Cv, where Cv equals to 5 over 2, so this is 2 over 5. This gives us 31.4 Kelvin. And plug in K1 here. We have P2. Well, now it becomes pretty straightforward. That's nRT2 over V2, and you can plug in numbers. Yeah, again, n equals to 1 times 82.1 times T2, 31.4, divided by 6000 equals to, that is 6000, 0.430 ATM. Okay. Now it becomes the most challenging problem for the entire exam, which is a derivation problem. So in this question, this one is pretty much the same example as we did in class on the van der Waals gas. So the easiest way to approach this problem is to take derivative on both ends. So we're asking about the compressibility chi, right? So we have 1 over Vm times the partial derivative of Vm over P at constant t. So I'll go really slow here for this problem. What we're doing here is taking the derivative on both ends of this equation with respect to P. Or when we write it out, we have the partial derivative of P over this entire thing. P plus A over Vm squared minus B at constant t. And on the right hand side, we're doing the same, but this one just gives us constant r. Now on the left hand side, we have a pretty complicated relationship here, right? You have something like P plus A over Vm squared. You also have like V squared minus B. And both of them have Vm in there. And what we have right now is like we want to have somehow a partial derivative of Vm in our expression. So let's set x equals to P plus A over Vm squared. And we will set y equals to Vm squared minus B. Alright, so this entire thing becomes x times the partial derivative of P over partial derivative of x times partial derivative of y over P at constant t plus y times partial derivative of x over P at constant t equals to r. So in this step, what we're using is just like the xy. Well, let me use something different. The mn equals to m dn plus n dm. This is just the basic calculus we're using. But we do not have dx and dy right now, right? We don't have an expression of dx and dy, and we do not have an expression of dvm here. So what we can do is taking the derivative of x over Vm. Now, obviously, in this case, we're assuming constant temperature. And dx over dVm equals to, well, we can't take this p out. And this gives us 2a over Vm third. All right, or the other way to put it is dx equals to dp minus 2a over Vm third dVm. Here we're just moving that Vm to the right end of the equation. And what about y? We can do the same for dy. So dy over dVm. Now this one is relatively straightforward. That just equals to 2Vm. Or we can write dy equals to 2Vm dVm. All right. Then what we're doing here is basically plugging numbers, right? You have x here. You have this dy, you have this dy here. You have y, you have y. You have dx, well, you have a dx expression here. So what we're doing is just plugging numbers. So x equals to p plus a over Vm squared times partial derivative of Vm, or in this case dy. So we have the 2Vm times the partial derivative of Vm over P at constant t, plus y, we're just plugging y, Vm squared minus b, and this x term here. Well, the first term, let's just write it out. So our dx equals to dp minus 2a over Vm third dvm over p at constant t, and this thing goes to r. That's organizing the terms a little bit. So first of all, let's write that 2Vm into the equation. So we have 2p Vm plus 2a over Vm. That's our first term here. Plus Vm squared minus b. And inside here, this term just becomes 1. Right, you have dp over dp. This term just becomes 1. And then you have 2a over Vm third dVm over dp at constant t, and this equals to r. All right. And then what we're doing is simply organizing the terms so we have an expression of this partial derivative Vm over p at constant t. So let's do this. In here we have 2p Vm plus 2a over Vm, and this thing will minus what we have here. QA over Vm third times Vm squared minus b times the partial derivative of Vm over p at constant t. And on the right-hand side, we want to move this 1 to the right-hand side. So we have r minus Vm squared minus b. All right. And in here, there are some of the terms that can cancel out. So we have 2p Vm plus 2a Vm minus 2a Vm plus 2ab Vm third times the partial derivative of Vm over p at constant t equals to r minus Vm squared plus b. So these two terms actually cancel out, and taking it together, we have an expression. So what we have here, we copy paste down to use our extra space. So what we have here is 2p Vm plus 2ab Vm third times partial derivative of Vm over p at constant t equals to R minus Vm squared plus B. Solve for this partial derivative. We got partial derivative of Vm over P at constant t equals to R minus Vm squared plus B divided by 2P Vm plus 2AB over Vm third. You can organize the term a little bit by times Vm third on both top and bottom. So we have R Vm third minus Vm fifth plus B Vm third 2P Vm fourth plus 2AB. And chi equals to negative 1 over Vm times the partial derivative of Vm over P at constant t, and that gives us, well, negative R Vm squared plus Vm fourth minus B Vm 2. On the bottom, everything stays the same. All right, and let's just copy this up. Okay, so that's our most challenging problem. And let's see, what else? 5-2. Express the molar internal pressure, partial derivative of U over Vm at constant t in these terms. So we give you a hint. We solve for the general expression of Cpm minus Cvm. As we say general expression, we're seeing this general expression of Cpm minus Cvm is not necessarily a ideal gas, and this process didn't specify it being an ideal gas. So this is something we solved in lecture 4. All right, and in this case, it's pretty easy to identify that this term is related to alpha, which equals to 1 over Vm times partial derivative of Vm over t at constant p. Or the other way to put it is this partial derivative of Vm over t at constant p equals to alpha Vm. So this thing becomes alpha Vm times du over dBm at constant t plus p. All right, and then we're just moving terms. So we have Cpm minus Cvm divided by alpha Vm minus p gives you the partial derivative of u over Vm at constant t. All right, so that's something we want. And this tells us something about the unit of our partial derivative, right? It's asking of our internal pressure. It's asking for our molar internal pressure here. So this one is the molar internal pressure. And what we want is, well, what is the SI unit for our internal pressure? And in this case, our pressure is the same as P, right? So this internal pressure partial derivative have the same unit as P. So the SI unit for P is Pascal, PA. All right, and that's everything. Let's see how long we take.